Okay, we're going to start by trying out some sample problems and applying Newton's laws using our 5-step process. Remember, we're going to draw a diagram, which is a free body diagram, and we're going to write down all of our forces and apply Newton's first, second, and third law to solve the problems. So let's go ahead and try out a few problems. We can break things up in two ways. We can either group everything together as a whole block of objects. We can take Sally and the scale together as one big fat object, or we can treat them as individual objects and break them apart. In the first way, we're going to, first of all, I drew a plus y axis. We're going to use a grouped object strategy. And so I'm going to take Sally plus a scale, and of course our total mass is going to be 50 plus 2 is 52 kilograms. Let's draw the free body diagram on this block. We've got the force due to gravity acting downward, which is mass times gravity. 52 times about 10 meters per second squared is 520 newtons. And we've got a normal force acting upward. And of course, we can use a little bit of Newton's first law math to work this out. So we have a static equilibrium in this case. And of course, if we add up all the forces in the y direction, we have our normal force acting upward and the gravity acting downward. And those will add up to 0, which means that Fn equals Fg, which is 520 newtons. Not a big surprise. We could have also used a Newton's third law approach to answer that, because this is our action-reaction pair, gravity acting downward and the ground acting upward. Let's take a look at a second approach using ungrouped objects and see if we get the same result. The thing that we're missing from up above is the forces that are acting between the girl and the scale, and between the scale and the ground. So we're going to take a look at the girl, and we're going to look at the scale separately. For the girl, we have force of gravity of 500 newtons, and we have a normal force of the scale acting on the girl, upward. Once again, we can look in the y direction. We can zero out our acceleration because we're not moving, and we can do a little bit of math. And obviously, once again, the normal force on the scale is 500 newtons, and the force due to gravity is 500 newtons. That's a Newton's third law action-reaction pair as well as using Newton's first law. Differs a little bit from what we saw above. We were looking up above at the girl and the scale as total acting down on the earth. Now we're actually looking at the girl standing on the scale, and you can see the scale reads 500 newtons as a result. And if we look at the scale itself, well, it has its weight of 20 newtons acting downward, and we have the girl standing on it, and we have the ground pushing back on it. And of course, all three of those forces have to add up to 0 because we are not moving in the y direction. And if we look at that, we can take a look and say, all right, well, that girl pressing down we already solved for in the previous case, which is 500 newtons using the third law, which means we have 500 pressing downward by the girl, 20 pressing downward on the scale. Therefore, the green arrow, the normal of the ground on the scale, must be the sum of those in Newton's first law because it's not accelerating. Sure enough, it's 520 newtons. And we can use the third law from up above. This is the action-reaction pair from up above. This 520 newton force actually matches the 520 newton downward force of the girl and the scale up above. So our action-reaction pair is actually here and here for that particular example. Now, let's just suppose that Sally's standing on the scale, and all of a sudden, let's suppose she lives in Florida, and a big sinkhole opens up underneath the bathroom, and all the ground drops away from beneath her. So what happens to Sally and the scale? What does the scale read, and what is the normal force in between? We'll assume y is in the upward direction as usual. And we're going to ungroup the objects in this case and look at each object as a separate entity, draw a free body diagram for each. So we have the girl and we have the scale. Now in the girl we have gravity acting downward, 500 newtons, just as before. And we have a normal force of the scale acting up on the girl. Don't forget, once the ground falls out from underneath these objects, we will have both the girl and the scale accelerating downward at negative 9.81 meters per second squared, which is negative g. So I'm going to look first at the y direction. Let me apply Newton's second law. And remember, we are not going to zero out our acceleration in the y direction. I think we are accelerating downward because we are falling. So if I substitute in for our sum of our forces, we have our normal force minus our gravitational force is the sum of our forces. We have two forces acting in the y direction, as you can see. And we have the girl's mass times the negative acceleration due to gravity. And remember, for Fg, well, Fg is just mass times gravity. And you'll notice what happens here. I have on both sides of my equation, I have mass times gravity and mass times gravity. So those cancel out. And I get Fn equals 0. Well, that's interesting. The normal force between the girl and the scale is 0, which means what? That means she feels no normal force, and she feels weightless, essentially. Remember, your only sensation of weight that you have is when you actually feel something pushing back up on you. So if you don't feel something pushing up on you, you feel weightless. Let's take a look at the scale in that case. The scale has gravity acting on it with 20 newtons of force, but don't forget that the scale is also accelerating downward, and the girl is standing on the scale. Of course, we already know from the previous situation that the normal force of the scale on the girl was 0. Therefore, the normal force of the girl on the scale must also be 0. It's an action-reaction pair. So once again, we have no normal force acting on the scale. So the scale doesn't even sense that Sally is standing on top of it, and it is just accelerating downward as well. And it, of course, feels weightless as well because nothing's holding it up. Now let's suppose we put Sally in an elevator on top of the scale. We've got two cases. First, the accelerate. Let's take a look at the first case where the elevator is accelerating upward at a rate of 4 meters per second squared. Choosing plus y in the upward direction again. The girl, she has a force due to gravity of 500 newtons. And remember, I don't really care about the scale in this problem. So we have gravity acting downward with 500 newtons, and we have a normal force of the scale acting upward in the girl. The question is, what is that scale reading? Is it the same or isn't it? Don't jump to conclusions here. Don't forget that the whole system is accelerating upward at 4 meters per second squared. So we have two forces in the y direction we have to add up. We've got the normal force acting upward, that's positive Fn. We have gravity acting downward, that's negative Fg, equals my mass times the acceleration in the y direction. That is not 0, so don't cancel it out. Force due to gravity is just mass times gravity, so I'm just going to substitute that in. I'm going to come up with a general equation. Feel free at this point, if you want to plug numbers in, we have a number. We know what Fg is. You can plug that in. You know what your mass is. You know what acceleration is. You can come directly to an answer using numbers. I'm going to do a general solution. I'm going to solve for the normal force. That's the force we really care about. What's the scale read? And the normal force is the scale reading. And so we have the normal force equals the mass times the acceleration of the elevator plus mass times the gravitational acceleration. You'll notice essentially what's happening is the normal force that she feels on the acting back on her on the scale is going to be a sum of the force due to the acceleration and a force due to gravitational acceleration. So we've got the elevator acting on her and gravity acting on her in unison. And as you can see, the elevator's acceleration acting on her, and there is force due to gravity acting on her, and they add up to 700 newtons. Okay, what happens if the elevator is going downward at a rate of 4 meters per second squared? Similar setup. So we have the same type of free body diagram. We have the acceleration y direction is downward instead. We're going to run through the same setup with our equations. And everything's identical to this point. And everything's identical here. I'm plugging into this equation. The only thing that changes is that I have negative 4 meters per second squared plugging in for the elevator's acceleration. So instead of adding 200 to 500, I'm subtracting 200 from 500 to get a 300 Newton result. And so now Sally feels lighter as the elevator accelerates downward. So we have an offsetting experience here as a result. Okay, new problem. We've got 3 boxes stacked on the floor. Let's find all the forces acting on each box. So first of all, we know that these are in equilibrium, so the sum of the forces in the y direction has to be equal to 0. We're going to pick positive y to be upward. And we can use Newton's first and third laws to actually answer these questions. And we'll do a combination of both to show you how to do that. All right, and what contact forces are we talking about between these objects? Well, those are the normal forces acting between the objects. We've got normal contact forces from A touching B and B touching A, B touching C and C touching B, and C touching the ground. We're going to treat all 3 of these boxes, A, B, and C, as one big 10-kilogram object sitting on the floor. Let's draw our free body diagram. We have gravity acting downward, mass times gravity equals 100 newtons. And our normal force, well, gee, we're not moving here, so guess what that normal force will be? It'll be 100 newtons, and we could use the third law to come up with that answer, or we could go ahead and work out the first law and add up all of our forces, set them equal to 0. You'll find out that Fg equals Fn as usual. I'm going to break apart the boxes into 3 free body diagrams, and it's usually easiest to start with, and you'll see later, and after we draw the forces in, box A is going to have the fewest forces acting on it. So let's go ahead and start to look at that one first. We've got force due to gravity acting on object A of 10 newtons, mass times gravity. And we've got a normal force of B acting upward on A. So B is pushing back on A is what that shows. All right. And so, well, this is easy math. All right. If these are the only two forces and we're in equilibrium, then this has to be a 10 Newton force. And we can either use first law equilibrium situation, write an equation to show that's true, or I can say, all right, if these are the only two forces, then we've got action-reaction pair here from Newton's third law. So let's move on to box B. We have gravity acting downward with 40 newtons. That's 4 kilograms times 10 meters per second squared. We've got a normal force of box C pushing back up on it. And how did I know that was bigger? Well, that's because we have a normal force of A acting down on B. And these two forces, the red one and the black one, the normal force of A acting on B and the force due to gravity, have to be equal and opposite of the force normal of C acting back on B, box C pushing back on B. So that has to be a 10 Newton force from the previous problem. We had 10 newtons from box B acting on A. Well, this is the Newton's third law equivalent. This is the normal force of A acting on B. This is an action-reaction pair. These are two red arrows. And of course, as I mentioned, the normal force of C acting on B has to equal these two added up together if we apply Newton's first law. The sum of our forces, that plus that plus that, has to equal 0. So these two have to be equal and opposite of that. Let's move over to box C. In box C, we have gravity acting on it. And then we have a normal force of the ground acting back on box C. And I notice I could draw these normal forces on the other side of the box. Typically, I like to show forces pulling on boxes rather than pushing, but 6 of one, half dozen another, right? And finally, don't forget, we have box B that's going to be pushing back down on box C. Of course, we know that this force is 50 newtons. We already figured out over this side, and we can use Newton's third law. This is an action-reaction pair, these two green arrows. If you look at this, then, well, if I have 50 newtons acting downward, and I have 50 newtons acting downward here as well, so the gravitational force is 50 newtons for box C, and the force of B acting downward on it is 50 newtons. Those two add up to 100, and they must be counteracted by the ground. That's what this shows. And we're using Newton's first law to show that. So how many action-reaction pairs do we see here? Actually, we have the two red ones, we have the two green ones, and we also have two blue ones. The two blue ones, you have to look back on the last page to see the pairing for it. All right, new problem. We have 3 boxes on a floor, and we're going to push them along the floor with a 90 Newton force. Find the acceleration of the forces acting in each box in the x direction. How fast are the boxes moving after you push them 10 meters, and how long will it take to move the 10 meters? I suggested to you here that we start by looking at the system's entire large mass moving, and you could also break it into 3 free body diagrams. I'll do both for you. So we're going to take all 3 of these boxes, and we're going to group them together in one big box. Of course, gravity is acting downward. Mass times gravity, 18 kilograms times 10 meters per second squared, is about 180 newtons. The normal force acting upward, use Newton's third law, or you could use first law to show that that's 180 newtons acting upward. Not too exciting in the y direction. We're more so considering the x direction, what's happening. In the x direction, we have a pushing force of 90 newtons. And in this starter case, we have no friction on the floor. In the next problem, you'll see we'll have to add friction. It'll be a little bit more interesting problem. So let's see what's happening in the x direction. We'll use Newton's second law. Now in the x direction, don't cancel out the acceleration in the x direction because we are accelerating. We're trying to figure out what that acceleration is. We only have one force on the left side of the equation, so we plug in our pushing force equals our mass times our acceleration. Solve for acceleration, just divide by m. So I'm isolating this. You could plug in numbers at this point if you want, and that's what I'm going to do. And you get the acceleration for part A is 5 meters per second squared. This has just turned to a 1D motion problem with constant acceleration that you can easily solve to get the rest to parts B and C and understand those. And those are the equations that I would use. Now let's take a look at these same boxes, but let's break them down into individual free body diagrams, and now we can see the forces acting in between each box, which is a little bit interesting because we had to take into account that we're accelerating, not just sitting here. So we're ungrouping the objects, and remember that we know from the previous part of the problem that we have all three boxes moving together at a speed at a rate of acceleration of 5 meters per second squared to the right. So we're going to use that as we solve this. And on our first thing we're going to put on the free body diagram here are the gravitational components. And of course, upward in each case we have the normal force of the ground acting backwards on these. And we could use a Newton's third or first law argument to show that those are as we see here. More importantly, let's look at what's happening in the x direction. We know that we have a pushing force on the leftmost block of 90 newtons. Now, we have an interaction between boxes A and B. They're pushing against each other, so we have a normal force acting between the two boxes. This is a great example of a normal force that's not caused by gravity. It's from one box pushing against another. This is a vertical interface between the two boxes, and so we have a normal force that happens in the x direction rather than the y direction. Of course, that same normal force, if I have B pushing on A, well, then A is pushing on B as well. Gee, you can guess what law we're going to use to figure that out. On the right-hand side of block B, well, we have block C pushing back on block B. And of course, that means block B is pushing back on block C. Now, like we did on the previous problems, it's always nice to start on the free body diagram which has the fewest number of forces. So I'm going to start on the right-hand block here. Let's go ahead and add up our forces in the x direction for block C. And of course that equals mass times the acceleration in the x direction. And we know the acceleration in the x direction is 5 meters per second squared. So in the x direction we only have one force, and that's the normal force between B and C acting. And that normal force has to equal, well, mass times acceleration, 5 meters per second squared times 6 kilograms, which is 30 newtons. So we know that that normal force from between B and C is 30 newtons. We use Newton's second law to figure that out. Of course, how do we get this green arrow over here, the force of C acting on B? Well, that's just Newton's third law. That's an action-reaction pair. These two are matching forces. That's why I color-coded them in the same way. We can look at this a slightly different way. I know that this block is accelerating at 5 meters per second squared, and I know its mass. Well, mass times acceleration then is 5 meters per second squared times 4 kilograms is 20 newtons worth of net force acting on this object. And that's what I'm showing here. So the net force acting here is 20 newtons. And we know the right-hand force, this green one, is 30 newtons. And if we have a 20 newton net force acting, then this force over here has to be bigger, and it has to be 20 newtons bigger. So we know that that force must be 50 newtons. And that's using a Newton's second law argument on that. The net force is the mass times the acceleration, so we calculated the net force, and then we can subtract to figure out what the missing force is. Newton's third law, let me bring that over to the other side on block A. That's also a 50 newton force. And once again, we can use the same type of argument. We've got an 8 kilogram mass accelerating at 5 meters per second squared, so 8 times 5 is a 40 newton net force that we must have on this object. A net force means the sum of the 50 newton force and the 90 newton force must equal 40 newtons, and sure enough it does, and that's a check of our work. This is a summary of the solution for the parts B and C, and you can go through that on your own. Okay, now we just changed the problem. Now what happens if we put the boxes on a normal floor? In other words, it has friction with a constant 90 newton force again, but now it takes 2.828 seconds to move the 10-meter distance. So based on that information, first of all, can you find the acceleration and the forces acting on each box? Now we can't ignore the y direction forces. We'll talk about why that is. And also, please find the coefficient of friction. All right. And in the previous problem, the y forces didn't really do anything for us, and we could pretty much ignore them. They weren't doing anything interesting. However, now we need them because a normal force tells us how much the force of friction will be. So we need to use those normal forces. So they will be much more important now. So first of all, you can use motion equation 5 because we know the distance that's been traveled. We know the initial position we can assume is 0. The initial velocity we'll assume is 0. And you can plug in the time, and you can actually back into the acceleration, which I did, and I found it's 2.5 meters per second squared. You can check me on that. So our acceleration of objects is going to be 2.5 meters per second squared. I'm going to use a grouped object strategy to solve this. So here's my object, and let's roll our forces. Of course, we have force due to gravity is 180 newtons. Our normal force is going to be, we're not moving in the y direction again, so we have static equilibrium. So that'll be 180 newtons as well. Our pushing force is going to be 90 newtons to the right. That was given. And we've got, now we do have a frictional force, and that's what we need to find. We need to find the UK. First of all, let's go ahead and take a look. We've got, I'm going to apply Newton's second law in both dimensions. And in the y dimension, we have 0 for our acceleration in the y direction because we're static equilibrium. In the x direction, we are not static, so do not cancel out ax if you're not static. We're actually accelerating. Let's add up our forces. On the left side, we have two forces. We have the pushing force in the right direction, and to the left, we have our frictional force, and that equals mass times acceleration in the x direction. In the y direction, we have our normal force acting upward, and we have our gravitational force acting downward, and they equal 0 because it's static equilibrium. I'm going to go ahead and do a little substitution here. FF equals mu kFn. That's a standard substitution you'll always make. And we're going to keep our AX in here because we are accelerating. In the y direction, I'm solving for Fn like we typically do. I'll shift FG over. Of course, FG just equals mg. And of course, I'll label our Fn up here as 180 newtons. Of course, we could have used a third law argument to show that it was 180 newtons as well. Moving on here, Fn, I'm just going to make a substitution. I'm going to, at this point, go ahead and feel free if you want, plug in numbers in here and come up with your solution. I like to do a general solution, as you know. So I'm going to go ahead, for Fg, I'm going to plug in mass times gravity for Fn. Those two are equal to each other. Then, I only have one unknown in here. I know what Fp is. I know what mass is. I know what gravity is. I know what my mass is. And I know what the acceleration in the x direction is. We calculated before. So I can solve from UK. So solving from UK gives us this expression. If I plug in, I get 45 newtons over 90 newtons, which is 0.5. So that's our answer.